Hello everyone, I'm Tanyaras from PSEforSPEED Company Limited, and I will give a short demonstration of some new features of ChemSub software. I will start with a brief introduction, then followed by 4 application examples. Please also view video 1 of this series for the main features of ChemSub. Part 1. Introduction to ChemSub. ChemSub is a tool for analysis of chemicals and their likely substitution in chemicals-based products and/or processes. It offers various options of the identification of hazardous or unsafe chemicals and suggests alternatives as safe substitutes of the flagged chemicals, taking into account economic as well as EHS considerations. ChemSub suggests safe application ranges of the chemicals with respect to their use in products as well as processes that manufacture or use them. The main interface of ChemSub includes 8 toolboxes, each with specific purposes of use. In the top row, starting from the left, we have a modeling toolbox, which is used for creating property models and storing new models in the model library. The second one is for data search and retrieval, which is used for the chemical analysis. Here you can see the demonstration of this toolbox from our YouTube channel on the topic of Software Tool for Chemical Data at Your Fingertips demonstration, or click in the link in the description below. The third one is a chemical substitution, which is used for the analysis of chemicals present in products and processes, which we will highlight. In the bottom row are property estimation toolboxes, which are used to estimate the properties of chemicals. And the last one is for refrigerant cycle simulation, which is a simulation model to analyze the performance of pure and mixed refrigerants. The process of chemical analysis and substitution can be summarized into 4 main steps, which are presented in this framework. Begin with step 1, which is used to define the problem in terms of the basic information, applications, and specifications, such as compositions of chemicals are given as input. If the ID of any input chemical is unknown, alternative chemicals need to be found and specified before proceeding to step 2. But if the input chemicals are known, we will continue to step 2. Step 2 is the product analysis. In this step, the identified chemicals in the product or process will be verified for known hazards or other issues such as ban or pop. After verification, the analysis will show the properties and hazardous effects, as well as if it is a ban or pop list for all chemicals. If any chemical has problems, PJ will be greater than 0. If PJ is 0, there are no problems, and the user will be guided to step 4. If a chemical is identified to have a problem, 1 will be added to PJ. This is repeated until all chemicals have been verified. Step 3 is where we find the substitute chemicals. If PJ is greater than 0, the user will be guided to step 3 to find alternatives that can substitute the flagged chemicals. This step is repeated for each flagged chemical. The alternatives for a flagged chemical can be found through 3 optional tools, namely the CMD tool and databases with collected measured data and predict data filling holes in database 6A. When alternatives for all flagged chemicals have been found, each alternatives are verified. If PJ is now found to be 0, then we can go to step 4 for the conclusion. The last step is property identification or step 4. In the last step, the product or process will be analyzed in terms of sustainability, LCD indicators, safety, and cost. After that, the result of the analysis can be exported in the form of an Excel report. Please note that this step is still under development. Here, we would like to introduce the ChemSub database structure. The analysis of the product or process is processed through 5 databases. Database 1 includes basic information and specifications of the chemical, which are chemical uses and chemical types. Pure property includes 65 properties of chemicals, such as primary property, environmental property, secondary property, functional property, and so on, which are in database 2, which is linked to ProCAMD. Hazardous effects include physical, environmental, health, and other hazards, which are in database 3. Ban and POPs chemical lists are stored in database 4. Moreover, there is a list of refrigerants, solvents, CFATs chemicals, and liquid chemicals, and amino acid in database 5. All of the aforementioned databases make up a total of nearly 1 million chemicals in the ChemSub database. Please note that the number in parentheses represents the number of the category for each topic. The underlined number in italics represents the total number of chemicals in each database. Next is part 2, where we will demonstrate the application of some of the new features of ChemSub through 4 examples. Example 1. Generate substitutes for NMP with ProCAMD. The objective of this example is to generate substitutes for NMP, where the ProCAMD tool will be used in step 3, as according to the framework I showed earlier. NMP is a solvent used in a variety of industries and applications, such as paint and coating removal, petrochemical processing, and engineering plastic coatings. However, NMP could cause irritation to the skin, nose, throat, and eyes. To find the substitution of NMP, the desired properties need to be listed, which will be used as constraints by the search algorithm. Since the search with database has already been shown earlier in video 1, we will use ProCAMD to find more alternatives. First, we start ProCAPD and then click on ProCAMD for solvent selection through CAMD, Computer-Aided Molecular Design. Then, give the desired properties, which I have discussed earlier, to ProCAMD. To save time, we have already entered the data for this demonstration. Now we will open the save file and show the specified desired data. Then click on General Problem Control to view the basic data to be specified, and also the non-temperature dependent properties. The property specifications are those from database search, properties that are similar to NMP. Next, click on Go on the green button. Wait until the run is finished. The summary result will be shown as a pop-up window. ProCAMD generated 1,214 compounds, out of which 249 were feasible. This generated 1,791 new compounds, out of which 518 compounds were feasible. Then close the summary page and wait until all the 518 compounds are transferred to the results section. Now use this button to move the compounds on the results page. Select InDB to highlight only those compounds that can be found in the database. Not InDB highlights compounds that have been created but do not exist in the database. All includes both types. For example, the compound number 51 and 52 are diols that were also found from a database search, and that were found to have no safety or hazard issues. More diols are 211 to 216 and 342. For any of the compounds, click on ProPred. This will automatically go to Pure and show all its properties. And also, if we click on the data bank, it will show the properties available for the specific in our database. Here is the example of Pure property. And this is what will be shown if we click on Data Bank, highlight the compound to see the available measured data. Next, we will solve the substitute search problem by adding more constraints, such as mixture property and phase equilibrium properties. Similarly, we will start ProCAMD and open nmp2.cam. To reduce the search space, Esters are excluded from the general problem control page, but mixture properties and azeotrope miscibility calculations are added. The non-temperature properties are unchanged. In the mixture properties page, we have added data in this page to check for solubility with water, because NMP is soluble in water, so the substitute should also be soluble in water. For the azeotrope miscibility calculations, we have added data to this page to make sure there is total miscibility or high miscibility with water, so the substitute can work like NMP in aqueous systems. Now, with the additional constraints, we will click on Go to start the CAMD calculations. Like before, when the calculations are finished, the summary page is shown as a pop-up window. Fewer compounds are generated now because esters are not included and new properties are added. The final list of feasible compounds shows 323 compounds. Compound number 29 is the same as compound number 51 from the previous run, so we have an acceptable substitute for NMP. The next steps would be detailed extraction process calculations and verification by experiment. The result confirms miscibility with water that can be seen in the miscibility table. Next is example 2, where a selected set of gases are analyzed. The gas molecules are small in size, meaning that it is not possible to see them with naked or unaided eyes. As a result, gas analysis is valuable for process safety considerations and emissions monitoring. The selected set of common gases are listed, and the weight percentage and chemical function are assumed, only for analysis purposes. A real gas mixture like this is unlikely to exist. The objective is to compare the hazard effect of each gas in mixture. To save time for the demonstration, now we will open the save file of gas analysis. Then we click Analyze to see the results. The result is generated as a pop-up window in the form of hazard analysis data and product or process data. According to the hazard analysis, phosgene has been flagged for health hazards such as skin corrosion and irritation, inhalation, carcinogenicity, and more. The analytical result for chemical found in the air, carbon dioxide, reveals that there is a health hazard impact for organ toxicity. However, the GHS category number 3 suggests that it may produce drowsiness or dizziness. This means that if phosgene is used, extreme care must be taken to ensure there are no leaks. This slide shows a summary of the hazards of all the gases. It is surprising to note that CO2 appears to be the least dangerous gas, followed by hydrogen. The two refrigerants are very dangerous if leaked. Methane is also dangerous, and its leak from the natural gas or other sources need to be carefully regulated. For the same reasons, release of hydrogen sulfide need to be carefully regulated. We have already mentioned the dangers of leaked phosgene gas. Next, we'll go to example 3, which is the chemical analysis of solvents. Here is a list of common solvents used in industry for different applications. We'll use ChemSub to analyze the hazards of each solvent. To save time for the demonstration, we'll open the save file. The analysis results show 1-isobutylpropane-2-ol does not appear in the list of hazard analysis, which means that it may not be harmful. Other solvents has been flagged for hazardous effects. For example, ethanol is less hazardous because the GHS score is 3, which means warning in case of usage similarly with the SSG class table. For use of ethylene glycol, one needs to be careful since it causes some health hazards. 1-ethyl 3-methylimidazolium tetafluoroborate is not very dangerous since the GHS score is not low. Because of the high level of the health hazards, 1-methylpyridone and hexadecane and isopropanol must also be handled with extreme caution, while NMP appears in a bad list and probably need to be substituted. Comparing the solvents again with a published solvent table from the GSK company, we see that some compound solvents appear to be more acceptable than others from the hazard database. Ethylene glycol appears to be very good, while ethanol is listed under environmental waste. Final conclusions on their acceptability depends on the industry where the solvents are going to be applied. For the last example is the chemical analysis of processed chemicals. Here we will highlight the case of very common process, namely the HDA process, which is a commercially available process used for the production of benzene from toluene and higher molecular weight aromatics. The reaction of the HDA process includes 5 chemicals, which are hydrogen, methane, toluene, benzenes, and 1,1-biphenyl. The chemicals found in this process are already listed in this table. The retrieved hazardous property of the chemicals are analyzed and presented in this table. What the data in the table shows is that this process to manufacture benzene needs to be very carefully monitored, as we are dealing with the dangerous chemicals. Except for hydrogen, release of any of the other compounds would be dangerous. Hydrogen and methane are flammable and aerosol compressed gases that may cause explosions. The product, benzene, and the byproduct, 1,1-biphenyl, must not leak out from the process. For more comprehensive, the process locations that must be monitored for safety and hazards are marked with stars on this slide. The product stream, represented by green stars, will be retained in storage tanks. As a result, leaks from this vessel must be avoided. Also, benzene is dangerous, so it must not leak out. The purged gas stream is represented by the orange stars. Benzene, toluene, and 1,1-biphenyl must not go out through these streams. Their concentrations need to be carefully monitored. The pipeline containing high-pressure compressed gas is represented by yellow stars, and the pressure must be monitored. As a result, applying to the HDA process. Based on that analysis, benzene, which is a product that must be stored in the vessel, has the physical dangers of a flammable liquid and must store in the certified closed containers, underground tanks, or above-ground portable tanks. The byproduct is 1,1-biphenyl. It carries a warning about the environmental harm to aquatic life, so release of this chemical through the purged stream must be avoided. The purged stream contains methane and hydrogen. According to the investigation, while the environmental hazards of hydrogen is acceptable, release of methane can be harmful. Toluene is a flammable liquid that is used as the reactant. Therefore, it also must be kept in the closed containers. ChemSub can generate a report like this that includes the process locations, which must be monitored in terms of hazards. Please note that this option is under development. And this is the end of the presentation. Look out for more videos on related topics. Thank you for your attention.